Let's take a look at some of the rules for calculating values of rotational inertia, the property that represents the reluctance of an object to rotate. One of the four rules, I guess I'd say, that I'd like you to keep in mind, and probably the most important one, is to make sure that you think about a system of objects as individual objects when you're calculating the rotational inertia. Don't try to put individual masses all into one lump. Look at each object within the system separately. So for instance here, I'm not going to add the masses of A and B together. I'm going to separately calculate I for particle A and for particle B, and then take those values of inertia added together. Or in this system here, where there is a stick that has some mass to it that is connecting objects C and D, I would have to separately determine the inertia value for each of the particles and then also for the stick, and then combine those together. All right, so if we are trying to find the inertia for an object that's just sort of somewhere within a system, like a particle, how do we do that? Well, one of the important rules here as we go to use that formula mr squared is to make sure that our values of r are measured from the axis point, which is labeled P in this diagram. Now, sometimes it's a little bit more straightforward to see where those distances would be. So for object B and C, the distances would just be directly measured to that P. But the one that we probably would need to be a little bit more careful with would be particle A, and make sure that we don't just look at the distance between A and B. A lot of problems will give us that distance. We need to go all the way from particle A to the point P, the reference point, the axis point. We'll see in a few minutes how that works out within an actual problem. Something else that's important when we're calculating these inertia values for particles is that inertia is always a positive number. So, when you take a look at this picture, you can see that particles A and B are on the left and C is on the right. So some people may think, oh, is inertia negative for some and positive for the other? Well, if you think about it, the formula shows us that that we're going to square the values of r. So even if you were starting to think, is there some sort of a negative sign in there? When you square any sort of negative value, it would be positive as well. Inertia values are always positive. We never subtract values of inertia. Kind of like mass. Mass values are always positive. Okay, and then the final rule that I want to mention is, well, what if we don't have particles? What if we have objects that have a mass that is extended over a larger space? And those are situations where we need to look up a formula. You'll be given that half sheet, or you should have it already, that describes the way we calculate I for various shapes, like hollow spheres or thin rods, solid discs. Look for those phrases, and but also check to make sure that they are not massless, or we're not told that the mass is negligible, or the radius is not, something that that we're asked to take into account. So just kind of watch out for situations where maybe they describe it as a sphere, but it's this very small sphere that we really want to treat as a particle. All right, let's take a look at an example here. So we do have some spheres here, but notice that they are just located at particular positions. They're not, the radius of those spheres is not given. We don't know a size. So compared to the dimensions of the problem, we are going to ignore the size of A, B, and C. We just want to look at where they are relative to point P and use the mr squared formula to determine a value for inertia. So taking a look at the information, the R value for C is probably the easiest to determine. It's given directly to us as a measurement from P. When we look at this, the length of the rod is 90 centimeters, so half of that would be 45. And so we should be able to determine that the distance from B to the pivot is 40 minus 20, or 25 centimeters. And then finally, we got to look at this next section here. And again, we know the distance between A and B, but that's not what I need. I need the distance between A and the pivot point P. So that's the half length of the rod. So I would use 45 centimeters in my calculation, making sure I calculate mr squared for each of the individual particles, and working in standard units. This is how that calculation would work out. Notice that if you mark up your diagram and determine all those distances and so forth beforehand, the calculation itself is very straightforward.